Good afternoon. So now we have reached the culmination more or less of the course, and because today we're going to start looking at the Kraichnan model for a turbulent flow. In other words, finally we are in a position where we can try to model turbulent transport by replacing the velocity field that would come, let's say, from the Navier-Stokes by a random field and see and make some predictions. Okay. So for this we will use the tools that we have learned, in particular understanding of the Stachnovich limit and what it means. So let's take it step by step. Okay, so this is called the Kraichnan model. And the idea is, as I said, you have a velocity field, which is a turbulent field, and you want to model it with a random field, which means you have some field now, which is somehow the velocity field, but which is fluctuating in time, and moreover, you want to take it to the white noise limit, because only then I can derive something. So of course, if you're not doing white noise, it's not so difficult to understand how to do this, right? You can use the smooth random functions that I talked about. Simply you take three functions for ux, uy, uz, and build it up with a sum of Fourier modes, truncate the Fourier series somewhere, put random coefficients for each of the Fourier modes, and you will have a random field. Okay? So that's as long as it's not white in time, because it's just some velocity field is changing smoothly in time, but randomly, because the coefficients of the series are random. Where it becomes tricky now is, again, if I take the white noise limit and say at every time I sample, I completely decorrelate. Right? So then how do I even make sense of a velocity field? Okay. So for this, we have to come back to what a velocity field means. So let's say you imagine a grid, right, on this board. Think about it in 2D. At any point, so when I say a velocity field, it means if I put some coordinate system, let's say I make a grid. At every point on the grid, I have a vector, which is changing in time. Right? And of course, the vector is also changing in space. Such a thing is called a vector field. But what does it mean physically? Right? So let's say at some point here, right, I have this grid. And at this point on the grid, I have some vector field. Right? Here I have some other vector. Right? So what is this vector really? When I say it is a velocity vector, velocity of what? So velocity means something is moving. Specifically, the velocity is the time rate of change of position, by definition. Right? But velocity of what, right? It's not of the grid point. The grid point is fixed in space. Yes? So it is the velocity of a tracer or a material point which happens to be at this position at the time of interest. Right? So imagine there is a point navigating through the fluid. So at a certain time t, whichever point happens to be at this grid location, that point is moving in such a way that its time rate of change of position is that velocity. Okay, so the physical meaning of the velocity at any fixed grid point is always tied to the material point that happens to come there, because the material point, by material point I just mean tracer, right, particle that is following the flow. It is those particles that are actually moving. The grid is fixed. Right? So once again, a way to think about it is think about particle image velocimetry. You have a fluid flow, you can release many tracer particles, and you can visualize the flow by looking at all the particles moving. Right? So at any instant of time, you can say, okay, here are my particles. At the next time instant, they move somewhere. You take the derivative and you'll get velocity vectors all over the place. Right? If you have enough particles, you can reconstruct a field. So that is, of course, the experimental PIV method, but that's also fundamentally what we do mathematically when we define a velocity field. Right? What we really mean is, yes, I'm looking at a fixed grid. At every point on the fixed grid, there's a vector that's changing in time. But the physical meaning of that vector is you attribute that velocity to the material point which comes to the grid point of interest. Okay? So keeping that in mind again, we can now define what do we mean by the Kraichnan field. Right? So by remembering that the velocity field is really the time rate of change of position of material points, we can say now that I'm interested really in something like this. Right? So if x is a position of a material point, capital X, right? Again, to note that it's something with a trajectory. So this is the position not on the grid of an actual particle. So if I have a normal velocity field, not yet white in time, I'll write dxi dt is equal to vi. Vi is now the velocity field. Sorry, I don't have to put this. Okay. So I is an index, 1, 2, 3. So xi is a vector component. So ddt of the position vector is the velocity vector. This is normal. But now I want to make this velocity a random field. As long as the random field is correlated in time, this is still okay. However, if this is now white in time, then remember, if you have this term, it's like saying zeta, right? This would now be a singular quantity. Its variance will be infinity when you replace it by white noise. To regularize it, I have to write it as an SD. Okay, so when I go to the white limit, I will want to regularize it by writing, let me call it regularization, right? So just as when I said, remember, dx dt is equal to zeta in the Brownian motion problem. The zeta was not well defined, right? It had infinite variance. It was delta correlated with, so I had a Dirac delta function, right? So then that was not good. I rewrote it as an SD, such that zeta dt became the nice Wiener process increments. So same thing we are going to do here. Of course, remember that I want a velocity field, right? So this is a velocity field, so it has a small x, which is the grid. Okay, so if I define a field, Vi will be a function of the spatial coordinates. But to make this appropriate for the particular particle, I need to evaluate small x at the location of the particle. Okay, sorry, I'm going back, but just to specify again, this is the usual ordinary differential equation for tracking particle motion. Right? Dx I dt is equal to Vi, but the velocity field wherever the particle happens to be located. Okay? So this is just a definition of the velocity field. Now, if this is replaced by a random correlated in time thing, you don't have to do anything. It's the same equation. But when Vi is white in time, then I want to regularize it. So I will write it as dxi is equal to Vi again dt. Okay, and then this whole thing, I can now say, okay, this is white in time, so when I multiply by dt, I get something regularized, which I'm going to call dui, which again I'll have to evaluate. So what is this dui? dui is a displacement field. Okay, so if Vi is a velocity, Vi dt is a displacement, right? So it's an infinitesimal displacement field. Just like in Brownian motion, right? So you keep the analogy with Brownian motion in mind, right? In Brownian motion, it's the same stuff, except there is no x dependence because you just have one number. Right? But even in Brownian motion, the velocity is infinite, right? It's ill-defined. So therefore, I write equations for the Brownian steps, and those steps will have dw here, which is a displacement, right? So and that displacement is well defined. It's just a Gaussian number. Same way, now I have the position increment of the particle is being read off from some displacement field which can vary in space. Okay? And the properties of this displacement field now I can specify in a nice way. Okay, so I need to specify, so this is now a random field. I need to specify its properties just as I usually do. So it could have some mean. This right, that depends. So if you saying I have a flow field which has no mean, right? It's a turbulence in a box, there's no mean flow, then this will be 0. But you can always say I have some flow with turbulence on top, then it will be non-zero. Okay, so it doesn't have to be 0. I'm more interested now in the correlations. Right, so this is equivalent to saying Vi, and therefore this can either be 0 or not. Right? That just depends on if I have a mean flow or not in the background of the turbulence. Okay, so that's fine. Now let's look at the fluctuations, the correlations. Right? So if I was working with velocity, I would look at this quantity. Okay, so why am I writing the correlation again? I want to model the velocity field with a Gaussian random field. Okay, so Kraichnan model, it's Gaussian. And it's white in time. These are the two specifications for the Kraichnan model. Okay, so it's a, if you like, simplest way to model the field. You say it's white in time and also Gaussian. So if it's Gaussian, I only need to specify first and second moment. Right? That's what I'm doing now. First moment, I'm saying you can choose either to be 0 or to be some function of space, it doesn't matter. Then I come to the second moment. So second moment now, because I have 3 components, I'll have this Vi, Vj, it will become a tensor, plus I have space. So I can, if I specify the whole field, I should specify correlation at a given point, x component with y component, and also correlation between velocity here and velocity somewhere else. Right? So in general, I have ith component of velocity here, jth component of velocity somewhere else. So the here and somewhere else is in this x and x prime. Okay, so this is a 2-point correlation. So I would have to specify this thing. And now what I would do is I'm going to use the fact, some more assumptions on the Kraichnan model. So first, we will use the fact that I'm going to have homogeneous turbulence. So if the velocity field has to be homogeneous statistically, it means that I should have no way to identify an origin. So when I look at, so homogeneity has to do with position, right? So if I'm looking at correlation at 2 different points, for it to be homogeneous, the only thing that should matter is the distance between the points, correct? So I would write this as Dij, okay, and let me write it first in general. Okay, this is the general statement. Then I'll come back to homogeneity, isotropy, etc. Okay, so if I was to specify the properties of the random velocity field, which is of course going to be ill-posed, right? But if I were to think about that, I would write it as some correlation tensor between I and j, right? Which depends on these 2 points. Okay, this is the general thing. Then we'll simplify it for homogeneity, isotropy in a second. So without specifying any further assumptions, a general way to write this is some correlation tensor between the I and jth component of velocity that depends on the 2 different positions I'm taking in the correlation. Okay. And what about the time? Oh, sorry, I didn't put time here. Right, so in general, I can look at a correlation at 2 different points at 2 different times. Okay, so I have ith component at position x and time t correlated with jth component at position x prime and time t prime. Okay, completely general 2 correlation. I have to specify this general thing in order to specify the Gaussian field. So I can write this I'm going to write this in the following fashion because I'm taking a white in time noise. So the time correlation is going to be delta correlated. So you have delta function t minus t prime. This is identical to the Brownian motion. Right? Then because of space, I have to add this spatial correlation tensor to it. Okay. So if you go back, you'll see everything is, the development is same as what we did for Brownian motion, only that I have the space dependence now. Right? So I start with the ODE. If this is white in time, I need to get a regularization where the increment of position is read off from a displacement field that is random. Okay? Because it's Gaussian, I want first and second moment. If I work with this Langevin type equation, I would have to specify the correlation of the velocity field, right? That has now a spatial correlation part and the delta function because it's white in time. This is not a regularized thing, right? So to regularize, I will look at the quantity Vi into dt. Right? And this, that means instead of writing this, what I'm really going to do is look at the displacement field. Dou uj at x prime t prime, okay. This is now going to be, again, it's the same thing, right? I've just regularized the delta function. If t is equal to t prime and 0 otherwise. Okay. So if you look at this, this is again like Brownian motion. Right? Only difference is I now have the spatial correlation tensor. Right? Otherwise, what we are saying is I have basically a Wiener process, right? Where the second moment of the Wiener process increments goes like dt. Okay? The only difference now is I also have spatial correlation because I have a field. So what this tells us is that in the Kraichnan model, where I am going to replace the velocity field by a random white in time function, what I'm really doing is at every point in space, I'm going to be tossing a Gaussian random number whose variance is root dt. Sorry, whose variance is dt, standard deviation is root dt. Okay. Or if you like, since I've got the dt explicitly here, right, when I write down this equation, dxi is going to be a field of Gaussian random numbers of unit variance, right, which are then multiplied by root dt, so that I get the correct behavior. So it's identical to Brownian motion, except now I have some spatial variation. So where Brownian motion, this is just one random number. Now I have different random numbers at different positions of space, right? And the amplitudes of these random numbers can have some spatial dependence. That spatial dependence, of course, is statistical because everything is fluctuating, but it can have some, it doesn't have to be uniform. So if this dij was just a constant, then there's no spatial dependence. I get back Brownian motion. But I can in general have some spatial dependence sitting in this dij. Okay, so now let's look at what is this dij, right? So far I have not used any more assumption beyond saying that my velocity field is delta correlated in time. So I have this delta function sitting here. And when I multiply the velocity field by dt to get the regularized incremental displacement field, the delta function regularizes so that I have this finite correlation with amplitude dt when t is equal to t prime, right? And if any other time, it completely decorrelates, it's 0. Fine, so now let me look at dij. So we are going to simplify it. First, let us look at homogeneity. So we're going to look for a velocity field that is homogeneous. Right? So then that simplifies this dij to being only a function of r, okay, where this r is the distance vector. So that's just saying that the spatial correlation tensor is such that if I take the velocity at two different points, only the distance between the point matters, right? Because everything is homogeneous. So that simplifies the spatial dependence part. Now when I come to this ij, right, that means different directions. That's where I can invoke, to simplify things, isotropy. Right? That means there is no preferred direction. And if that is true, I and j should be interchangeable, should be symmetric. So that further simplifies the description. Right? So this must have the form of delta ij, so that it's basically identity matrix, right? And then another term that I can have, which still preserves the symmetry, is the following. Okay, so I have a tensor dij which I should specify as a function of r. Okay, I can further simplify it to specifying two sub-functions which don't have any ij, so they are just scalar functions, right? So the tensor part is sitting in delta ij and xi xj. These are tensors, right? They don't have r dependence. The r dependence factors out into two scalar functions now. Okay, and now I have to specify what are these scalar functions. Okay, so the behavior of these scalar functions will decide the dependence of dij on r. And this is where I will now use my understanding of turbulence phenomenology. Right? So some dependence I have to give on separation. Right? So if the 2 points are very close to each other and I'm increasing distance, how will the correlation change in r? Right? And if they're far away and I'm increasing distance, right? Again, similarly, what's going to happen? So based on what we did in the last class, we know that I should distinguish between being below Kolmogorov scale, where the flow is smooth, and above Kolmogorov scale, right, where I will be rough. So we will say that when r is smaller than the Kolmogorov scale eta, right, but greater than 0, right? So basically I'm going to have, so I'm just going to specify, I mean for both of them, right? So let me put dij of r is going to go like r square. Okay, because the velocity field is smooth, so remember dij is like v square, right? So if each v is going like r, then you will get this r square behavior. So it's basically smooth, and if R is beyond the eta, then I'm going to have something rough. Okay, so I hope this is clear. So the idea here, remember, Dij is giving me the dependence of correlation between the velocity Vi and Vj at a separation r. Okay. I can derive this by taking the variance of the increment, which is the difference. So if I taken this V minus this, right, multiplied by itself, I would get Vi square plus Vj square plus 2 Vi Vj. Right? So, and I have Vi Vj. So the product can be related to the variance of the increment. Okay? And so if the increment goes like r, its variance will go like r square. Right? That's how we get r square. Okay, so r square will give me a smooth flow. And if zeta is less than 2, I'll get a rough flow, right, which corresponds to the inertial range. And if you want to reproduce the Kolmogorov behavior for transport of tracers, then zeta has to be 4/3. But you can use other values to mimic other kinds of roughness, right? That is done just for gaining understanding. So the Kolmogorov value of zeta is 4/3, but anything less than 2 will give me a rough field, right? So that's so because I want it to be smooth, I'm saying if r is below my dissipation scale, it will be r square. That will keep my velocity field nice and differentiable. And above that, I would take something rough if I want to mimic turbulent flow. Yeah.
The condition for isotropy, what is x square and then denominator in the second term of the analysis?
So x is the magnitude of the vector. X vector. X is the position vector. No? So this is the vector, right? I'm taking a xi component or xj component. X is just magnitude of xi.
Either of xi or xj, or do we have to choose xi?
No, x is the same vector. Xi just means the ith component with a jth component. No? Oh, sorry. So my bad. Yeah, there is no x here, of course. What I meant is Ri. Yeah, thank you for that. Ri, Rj, R square. Sorry. Sorry. Yeah. So it depends on R, of course. So I'm saying it's. Yeah. So I can build. So R is, of course, a position vector, right? And this also satisfies this because it depends only on R, right? So this has no dependence on the magnitude, only on the direction in which I take the. No. For so this is what you get to get the Richardson cascade. That's super diffusion. That happens in the inertial range. Right? Yeah. No. That is for eta. You always have so forget about this now. Super diffusion happens in real turbulence. Okay. In the inertial range. If you want to mimic that here, then you will get super diffusion only above the Kolmogorov length. That means in this portion. If you want to get that same Richardson law, right? So where the displacement, mean square displacement goes like t cube, then this zeta has to be 4/3.
Below the Kolmogorov scale, there would only be diffusion.
No, below the Kolmogorov scale, it's smooth. No, it won't be diffusion. It will be separating exponentially. That's what I said. No? Then you can write an ODE for the separation. If you have two particles in a constant velocity gradient, they'll separate exponentially, not diffusively. No?
Turbulence becomes immaterial because below the Kolmogorov scale.
Yeah, you just see a laminar flow, time-dependent laminar flow. Right? So, of course, the velocity gradient is changing in time because you're turbulent. So then you can say, I'll separate exponentially with the Lyapunov exponent of the turbulent flow. When I cross Kolmogorov, then I'll have this explosive behavior. That is going to happen here. That will happen for any zeta that is rough. That means any zeta less than 2, you will have that kind of explosive separation. If you want to get exactly that t to the 3/2 behavior for the amplitude of the distance, then you have to do 4/3. Okay. So I won't go more into details of this. We won't be using it in the rest of the class. Okay, so the main point so far is that in the Kraichnan model, we replace the velocity field, right, with really a displacement field because we will want to regularize it. So the way to think about it is that if I am following a tracer in my turbulent flow, the increments of the position of the tracer is determined by a random displacement field which is standing in for the turbulent velocity field. And I can specify the first and second moments of this random field. Right? The second moment basically becomes a correlation tensor. And that's what we specified. Okay, now what I want to do is, so this is just a definition. From this, I can now derive some interesting results, which is what we are after. So the whole course from the beginning has been stochastic and turbulent transport. So as I had said in the beginning, we want to get some understanding of how mass transfer will occur in a turbulent flow by replacing the flow field with a random field to account for the fact that the turbulence is fluctuating. Okay. So that's what we'll start doing now. So the first thing I can ask is, how will a tracer move in the flow? Right? What kind of behavior will it have? So you've already written the equation for it. Let me write it again. Okay. So we say that the increment of the position of the tracer is basically read off from the displacement field. That means this is a field where the position vector is determined by the position of the particle. Okay. This is capital X, this is small x. So the first question is, so this is like an SD, right? If I want to find out what step I should take, I simply look at my, so let's say I'm at some position here, underlying me is a field. At this position, the du will take some value, and I take that step. Now I go to a new position, time has also changed, I'll have a new value for du, I take another step. Okay. So it looks like basically like random walk where I'm taking random steps, except that what step I take depends on space because the underlying random thing is also a field. Okay. So that means, yeah, so that is the point. Now, first question then is this a Ito or Stashnovich SD? So rather, even before that, is it a additive or multiplicative noise? So here I have the variable dxi. This dui is a random number, right? It's the noisy part. Is this additive or multiplicative? In other words, does the effect on xi depend on the position? Right? So the generalized definition of multiplicative, so the simplified way is if you write an SD, you have a Wiener process dw, you look for the coefficient and see is the coefficient dependent on x. Here I don't have that, it's not written right now in that style. Right? I'm saying there is some field. But to generalize the concept, does the increment I'm going to take depend on the position xi? The answer is obviously yes, right? Because that's where the spatial dependence comes in. So if I'm at the same time and I have particles in two different places, right, they can take two different steps if my field has some systematic dependence on space. Correct? So clearly it's multiplicative. So now that we know it's multiplicative, we have to say, am I going to take the Ito interpretation or the Stashnovich interpretation? Right? So what does that mean? So suppose I was to actually discretize it, right? So right now I've just written it in this notational form. So if I were to discretize it, say delta xi, I would have delta ui, correct? So I'm thinking about, suppose I were to write a numerical scheme. Now multiplicative, what x should I take? Should I take xi? But that would be at the beginning of the interval. Correct? So let's say I'm updating my particle, I'm at xi now. I want to find delta xi, the new step. Okay. So where should I evaluate the displacement field? Should I evaluate at the beginning, xi, then I'm in Ito? Or should I do this? Then I would be Stashnovich. Or I can do something else if the Stashnovich is not correct. Right? So you see, once again, because I have the noise depends on the variable, right? So the noise depends on where I am because the noise is a field, right? Or because the noise field is being read off at my position. So then I have to say, which position am I going to take? If I'm going to take a time step of delta t with a corresponding step of delta x, at what position in that time interval do I evaluate the displacement field? Because if I take smaller steps, I will get different values of ui, correct? The same notion behind multiplicative, right, and Ito Stratonovich. Okay, so the question is now, what should I do, right? Should I take the Ito interpretation or should I take the Stratonovich? What is correct? Okay, so because we know that there can be an infinity of choices, right? This is the equivalent of specifying what stochastic integral. So that's why now we can use what we have done in the past several lectures in trying to understand what is the correct limit, right, of a White and time process. And what did we learn in the last class? We said that any one-dimensional process, first of all, if you start correlated and take the white noise limit, you will get Stratonovich. Right? So if I write an SDE which is multiplicative, I should take Stratonovich if I am interpreting it as the limit of some correlated fluctuating process. But this is now not one-dimensional, right? Why? We are in fact multidimensional for two reasons. We are first of all multidimensional because I have three components if I'm in a 3D velocity field, right? Or two if I'm in 2D, doesn't matter. So because of this subscript I have multiple components. Then I'm also sitting at different positions in space, correct? So if I think about, I can break up this simplified notation in detail, right? I can imagine that for simplicity, I discretize my space on a grid. I take 1,000 points on the grid, right? So this field is really built up of 3 noises at every point at 1,000 points. So I have 3,000 noises, okay? So if I to rewrite it in the style of the SDs we've been doing from the beginning, right, as a single vector, I would say the change in position vector, right, is equal to some function that samples the field times the vector of noises. Okay, and that vector of noises is obviously a vector, it's not one noise, right? It's 3,000 noises. So if you like, I have to write a long vector dwi in Wiener increments, 3,000 of them, because 3 for each spatial location and 1,000 locations. And this must be multiplied by some kind of tensor which will pick out the noise at this position. Okay, so that is the coefficient. So the coefficient function somehow picks out the correct noise, but it's multiplying a huge vector of noises. So my noise is multidimensional. Okay, so now if I want to answer the question of interpretation, I need to think of it as a multidimensional noise process. Right? And what we learned in the last few classes is you will get Stratonovich only if the correlation matrix of those noises is symmetric. So now let us go back to what we had written here. So I have these 3,000 noises, right? They are noises at different points, and at each point I have 3 noises, right, for x, y, z. So I can take any component at any position with any other component at any position. This will be 2 noises. And the question is, correlation of this with that, is it the same if I flip it around? Right? Then the matrix will be symmetric. Right? So that we can understand from here. So first question is it symmetric in I and j? The answer is yes, because I'm assuming isotropy. Right? So I can take any x component and y component, y and x, it will be same, right? Because there's no difference between x, y, and z. So this I and j index, it's symmetric. Right? Then what about the 2 positions, any 2 positions? So if I say what is the correlation of this with some other point forward in time, right? Is that the same as that point with this forward in time? The answer is yes, because it's a homogeneous field. The only thing affecting the correlation is the distance, not the absolute location. So I can interchange x and x prime. It will make no difference. Okay? So because my field is homogeneous and isotropic, the correlation tensor of this huge vector of noises, right, will be symmetric. So that is not the same as this correlation tensor. Right? This is what I'm trying to hammer home. So the way we had derived it, we derived for a situation where you have some matrix multiplied by a vector of noises. So I'm saying I can take my field of noises and rewrite it as a big column vector with some coefficient matrix. I can always do this. And that column vector, if I take its correlation matrix, right, that will be symmetric. Why? Because it's made up of different components. Those components anyway are symmetric. And different positions. Those positions also are symmetric. I can interchange them as long as the distance is same. So this means the correlation matrix is symmetric for the homogeneous isotropic Kraichnan model. You can already see that when will you break this assumption? Immediately when it's not homogeneous. Right? So if you imagine a channel flow where the turbulence is less near the wall and more at the center, and there is some physics like the fluctuations first build up at the center and then go to the wall and die, for example. Then when you look forward in time, the correlation of center to the wall will obviously not be the same as wall to the center, right? Going forward in time, because it's only the wall that is the center that is feeding energy to the wall, for example. So then you will break this assumption. I will not be able to proceed in the way I'm about to. But as long as you say homogeneous isotropic, I know that my correlation matrix of this whole, all the noises sitting in this field are symmetric. So therefore I can say it's multiplicative and Stratonovich. Okay, but it will not be Stratonovich unless I am homogeneous and isotropic. Yeah, I'll reinforce this point about thinking about it as a vector in a second. But I hope at least you can see that I want the correlation of all the noises to be symmetric. Clearly it will be, because I have two kinds of symmetries being enforced, right? I have isotropy, that means x, y, z components are all interchangeable, and homogeneity, so all positions of any 2 points are interchangeable. It won't affect the statistics. So you can see that there is no way in which there can be any asymmetry, because I put in all possible symmetries in my field. So it's multiplicative, and the correct interpretation is Stratonovich, which means if I had replaced the velocity field initially by a smooth random noise with some time correlation, then I just solve an ODE for the position of the particle. Now, as I make that time correlation smaller and smaller and hit white noise, the limit I will reach will be this equation in the Stratonovich interpretation, which means that if I were to actually do a simulation to discretize, I will have to write it like this, right? So the increment will be the displacement field evaluated not at my starting position, but at the intermediate position. Now, of course, I can't do this in a simulation, right? Because I don't know dxi. I'm trying to solve for it. So I'll have to convert Stratonovich to Ito. Okay. So the way I would like to write this is I'll put an S here to indicate that x is evaluated, this position is taken from the particle's position in the Stratonovich interpretation. And the implication of that is this. Okay, so then if I write it in that style, I can say that the Ito version. So now we want to try to find the Ito version of this, right? So if I write this is Stratonovich, if I remove this, I'm saying Ito, but then I have to complement that by saying okay. So there's a nomenclature, so I don't have to put deltas and so on. Sorry, D. So this should be recognizable, right? It's just the usual thing. The Stratonovich is the Ito where I evaluate earlier the coefficient at the midpoint, but now I have to evaluate the whole field of noises at the midpoint, right? Because the dependence on x is sitting inside the field. It's not sitting out as a coefficient of the noise. Any questions? Okay, so hopefully it's clear that I have this field. It depends on where my particle is located, because I have to read off the field at that position. So therefore I have to decide what particle at what time to evaluate the particle position. So it's a multiplicator. And I should use a Stratonovich interpretation and evaluate at the midpoint for the reasons we proved in the last few classes, right, in taking the white noise limit. So therefore I have reached this position. Now I would like to extract out this dx by 2 to convert it to an Ito equation where all the fields are evaluated only at the starting point. Now, normally we use a Taylor series, right? Remember when we went from Stratonovich to Ito, we did a Taylor expansion and used the Ito rule that in the mean square limit, you only keep the second moments of this dui, but any dui dt will be 0, dui to cube will be 0, right? So when we do that, we could simplify it and get the Ito equivalent. Right? But right now, it's not clear for me that it's not immediately obvious how to pull out this dx by 2. You might feel that why not just do a Taylor series expansion. The intuitive thing would be, okay, I want to extract this out. Let me do d by dxi of this, this at the starting point plus gradient of this into dxi by 2, right? That seems clear. But let me just be a little careful and first show you how we can think about this vector field in the usual framework that we have adopted to study SDs, right? So the way to do it, I would like to extract out the spatial dependence from the noises. So I can choose a basis set. So let me choose a basis phi n. Okay, so I put superscript n. So the superscript is for the number of the basis function. Okay. So I'm going to say that I'm going to choose a basis set to represent my physical space, okay? And I want the basis set not to be some kind of Fourier series, which the function should not be defined everywhere. I want it to be 0 everywhere except in some small location. So a simple thing could be like a series of pulses, right? So this is, for example, phi 1, and then phi 2 is 0, and then non-zero somewhere else, right? For example, right? This is phi 2, and so on. So this would be a simple way to do for example, it would be equivalent to taking grid points. Right? I can always do this. I have some function. Right? This dui is some function of space. I can write it as a sum of basis functions, where the basis functions are like some localized thing. I'll tell you why I want it to be localized in a second. I don't want to use Fourier series as a basis set. We'll see why. Okay, so anyway, the point is I have now a sequence of functions. This is a vector, phi n. So n equal to 1, 2, 3, 4 are the different basis functions. So the space information is there, and I can reconstruct the field by summing them up. Okay, so I would write then my field du I so du I means I have x component, y component, z component. For each component, I will have a corresponding basis set, right? So I'll have a basis for phi x, phi y, phi z, and each of those will have n. And so each of these will have noises. Sorry, n. Yeah, that's better. Okay, so the idea is now I have some basis set, okay, which represents my dependence on space. Okay. In fact, maybe the simplest thing is to just write it like this. Yeah, I think maybe this is the best. Okay. Yeah. So what I'm saying is now I have a field, right? dui. Keep the I aside for the moment, right? So I have some field du. Instead of specifying it, I can write the field as coefficients times basis functions. Okay. So dui is the sum of the nth basis function with the nth coefficient, right? And the repetition of n means I have to sum over them. So I can reconstruct the field by summing up the basis functions with coefficients. And the point is those coefficients are random. That's why I put the Wiener increment there. Okay, in any other, this is going to be normalized, so the amplitude you can put inside this. Okay, so these are basically random numbers. And now, because I have x, y, z, I can toss more different random numbers. Okay, so this is a matrix, but I could always rewrite it in a vector. There's no problem. Okay, so the point is the spatial dependence now is sitting in the basis function. Yeah, sorry. Okay, so now when I want to evaluate dui in this Stratinovich way, right? It will be equivalent to evaluating what? Not the noises are separated. I'll just have to, this is the coefficient now. This is the coefficient, right? I'll have to evaluate the coefficient, which is a function of x, at the x plus dx by 2. So now it looks more like what we have seen before, right? So if I put this here, it will look like a multiplicative noise. Some coefficient of x, right, times linear increments. And therefore I can take to do the Stratinovich from Stratinovich to E2, I can take the derivative of this, which is smooth because these are basis functions. Okay. So this just tells me that it's okay for me to do the obvious thing, which is to directly take the derivative of this field and to do a Taylor expansion. Because that would be equivalent to if I wrote this field in terms of basis functions, I could take the Taylor expansion about the basis function. The noises are all sitting out separately. You can also see now what I was talking about correlation, because if I rewrite the noises in this way, right, then this is a matrix of x sitting in front of the linear increments. If I take a correlation, what I will want is the I and j's to be symmetric, which I know they are, and this phi of x, right, to be homogeneous, which is also the case. Okay, anyway, so this was just to tell us that I can directly take the derivative of phi of x, right? So that it's justified for me to apply a Taylor series expansion here. The other point was, why did I choose a localized basis like pulses, right? Because now if I'm going to say, remember now the tensor has changed to I comma n. Okay. So then if I do the noise at different positions, I don't want to look at correlations between different basis functions, the coefficients of different basis functions. Okay. Because those need not be symmetric. So to avoid confusion, let me write, this need not be the Wiener increment. Let me write it like this. So this dA is some noise. Okay, so in other words, it's a Wiener increment, but it can have different amplitudes depending on n. Right. Now the point is, I have changed the noise to a matrix of dA in. And the question is I and n symmetric? Okay. So I know the I is symmetric because that is x, y, z. But what about n, right? N corresponds to now the different basis functions, because these are the noises of different basis functions. And if I want symmetry, I would have to say, is the correlation between the first basis function symmetric with the 10th? And this will not be the case if I use Fourier functions, because then the first function has got large length scales, nth function has smaller fluctuations. That thing will not be symmetric. Right? But here what I've done is used a local basis. So the function 1 is just a pulse at some location. Function n is at some other location. This is like, again, saying two different points. Right? And that will be symmetric because of homogeneity. So the point is, it's possible to write the displacement field as a summation of basis functions in such a way that the coefficients of the noises, which are now just amplitudes of the basis functions, remain symmetric. So therefore, it's still fine to use the Stratinovich interpretation, which is not clear to see if I think of it as a Fourier decomposition, because then the noises are coefficients of Fourier functions, and obviously large-scale Fourier functions will not interact symmetrically with small-scale functions because there's a cascade of energy. Right? But here I'm still retaining the localization in space. Right? So the nth basis function is just some pulse here, and the first basis function is some other pulse here. They will interact symmetrically. Okay, so the upshot of all of this is that I can continue with the Stratinovich interpretation and do the obvious thing to go to Ito. So I'll write this as dui at x now. That's like evaluating it at the Ito. Again evaluated at x. Okay, so you see I have dxi is dui in the Ito interpretation plus dou by dou xj of the displacement field, again in the Ito interpretation, multiplied by dx by 2. Plus the higher order terms, but when I use Ito's rule, they'll cancel out. Right? So this is the lowest order stuff that will survive. So we did the exact same thing when going from, as a working rule, when going from Stratonovich to Ito. Okay, so now I just have to replace dx by again, right, dui. So I'll have dui here plus dou by dou xj of dui right, this whole thing into duj. Sorry, dxj I have to put in. Right, so dou by dou xj and therefore dxj. And dxj I replace by the original equation, which is duj. Right, now here in this equation, it's at the midpoint. Right, but again, because I am using Ito's calculus, if I again expand it, I'll get higher order terms that will vanish off, right, when I use the Ito rules. So this will be what will survive up to order dt. Okay. So this is fine. This is just saying that it's the Ito part of it, right? Ito interpretation. Now this is the extra drift term that I've got. But now I need to evaluate it, and remember again in the Ito rules, I need to replace the product dui duj with the correlation, right? That capital Dij dt. But right now I can't do it because this is sitting inside the derivative. So I would like to bring it inside. This is j. Sorry. Okay, so d by dxj of dui, and then I'm multiplying it by a duj. Okay, so I need to deal with this. But this is actually the same as writing half right minus maybe it's better to write it like this. Okay, so I just use chain rule and I pulled the duj inside and compensated for it. Is that okay? So now you see I have dui duj, which I can replace with the correlation. Right? But what about this term? Now this you will see, interestingly enough, is just, so this would normally give me an extra drift, except for the fact that, what is this? It's nothing but divergence of the velocity field dt. Right? So if I'm looking at an incompressible flow, it's 0. So of course you can use Kraichnan for compressible flows also, but if we limit ourselves today to just looking at an incompressible flow, that means solution of incompressible Navier-Stokes, then this is nothing but related to the divergence of my velocity field, right, which will be 0. So that's something I didn't mention in the beginning, but our displacement field should also satisfy this requirement. Okay, so if that is true, I'm modeling it as incompressible, then I can discard that, and all I have is this. And dui duj is what now? Remember now, this is the correlation, right? So let's go back. Here we are, right? dui duj is dij dt, right? If I'm at the same time, so I'm at the same time now, okay? And I'm also at the same position in space. That means x prime is equal to x. That means r is equal to 0. So in the end, I should get these terms with r equal to 0. So that will drop this guy off, right? And then I will get just this term, right, with delta ij. So d tilde of 0 is some constant. It's not a function of anything, right? It's evaluated at no separation. And delta ij means I can just write this ultimately as dou by dou xi, which is just the divergence of But this is obviously 0, right? Because this is not a function of space. That was a consequence of homogeneity. If I said my statistics are varying in space, then even the single point statistic, which is, so this is just the variance, right? It's Vi, Vj at the same point. That means it's just the variance of the velocity. And if the variance of the velocity doesn't depend on space, because I'm saying statistics are same, then this is just a constant, and this must be 0. Okay, so the result we have derived is for incompressible, homogeneous Kraichnan flow field, the Ito and Strachanovich interpretations are same. Okay, but that's only when it is incompressible. If you use a compressible field, then this will still become 0, but you will get this extra term here. Okay, which is associated with the divergence of the field. So then I would have the Ito version of the position trajectory equation would be that the change in the trajectory is the displacement field plus the displacement field into a correction which has to do with the divergence. So in other words, it's the displacement field multiplied by some coefficient which has a correction due to the divergence. It's not 1. Okay, so this is our first kind of subtle result, right? That if you were, so what this means is, as long as I said, right, you replace turbulence with a correlated in time flow, no problem, just evaluate trajectories of particles the usual way by solving dx dt is equal to v. When you do white noise, you see now we have some subtlety. To get the correct results in the limit, if it's incompressible, you can just solve this equation. That means you just read off the displacement field, take a step, take a step, take a step, do Ito. First order Euler method, right? But if the flow is compressible, and if you just do this part, you will get wrong results. You need to account for a correction which comes from the compressibility, which is of course a completely non-obvious thing, right? But because we know stochastic calculus, we are able to derive this properly. Okay, so you would have this correction sitting here, but if it's incompressible, it knocks off.